In this video, we will learn how to identify redox reactions and write ionic equations to describe electron transfer between oxidants and reductants. We will only look at redox reactions of atoms and simple ions, and not covalent compounds or polyatomic ions. This is an atom of hydrogen. An atom of hydrogen typically has one proton and no neutrons in its nucleus, and a single electron in its electron cloud. To help us keep track of the electrons, we can use an electron shell diagram, with one electron in the first electron shell. An atom of hydrogen can gain one electron and become a hydride ion. It's the same number of protons, but one extra electron. Alternatively, a hydrogen atom may lose an electron to form a hydrogen ion. It can help to simplify this diagram by writing H+ instead. When atoms or ions gain or lose electrons, they change their chemical behaviour, so it's quite important to keep track. One of the ways we can do this is by talking about reduction and oxidation. Reduction is the process of gaining electrons. It can be 1, 2, or any number. So, we say that a hydrogen atom is reduced to form a hydride ion because it gains one electron. The opposite process is called oxidation. Oxidation is the process of losing electrons. For example, we say that a hydrogen atom is oxidized to form a hydrogen ion, losing one electron. It's not immediately obvious from the words which one means what, so there are a couple of mnemonics that may come in handy. These are oil rig, or you can use Leo the lion says grrr. It doesn't matter which you use, they both mean the same thing. Oil rig expands to oxidation is loss and reduction is gain. And Leo the lion says grr means that the loss of electrons is oxidation and the gain of electrons is reduction. These definitions of reduction and oxidation are useful for atoms and monatomic ions, where we can see the charges. For polyatomic ions and for covalent compounds, we need to use oxidation numbers instead, but that's beyond the scope of this video. But there's something slightly strange. Where did these words come from? It doesn't seem to make sense for reduction to involve adding something. Well, it all comes down to the fact that oxidation used to be much more specific a word. It used to mean reaction with oxygen. When we react magnesium with oxygen, we form magnesium oxide. So we have oxidized magnesium. If we find the right chemical, we might be able to remove the oxygen and form magnesium again. And historically, we'd call this reduction, removing oxygen from an oxide or peroxide. Now let's have a closer look at magnesium in its pure form and in magnesium oxide. The atoms in pure magnesium have zero overall charge. They're neutral. But magnesium oxide is an ionic compound. We have magnesium 2+ instead of magnesium atoms. So when we oxidize magnesium, we're taking away electrons from the magnesium atoms. And when we reduce magnesium oxide, we're adding them back. So reacting with oxygen does exactly the same thing as what we've described before, oxidation being the process whereby electrons are removed. And it's the same for reduction. When we remove oxygen from magnesium oxide, the net effect for magnesium is that it gains electrons. And this is where the word reduction comes from, removing oxygen or reducing the amount of oxygen. This leads to a neat trick. When we see a substance reacting with oxygen to form some kind of oxide, that's oxidation, and electrons are being removed. And if we see some kind of oxide losing oxygen, then a reduction is taking place, and electrons are being added. Be very careful to remember that it's not the oxygen itself we're looking at when we're looking at adding or taking away electrons. It's whatever it's bonding to or leaving. So in this case, we're just looking at electrons being added or taken away from magnesium or magnesium ions. There's a neat feature of chemistry that we can rely on. Electrons rarely add to or leave an atom or ion spontaneously. The reason they move is usually because there are other reacting chemicals around it. For example, let's imagine we have a stable arrangement of hydrogen molecules and a lump of lithium. When they get too close, electrons will be transferred and will form lithium hydride, which is made of lithium ions and hydride ions. At some point during the reaction, for each lithium atom, the outer electron has jumped over to a hydrogen atom. So the hydrogen atoms were reduced, they gained electrons, and the lithium atoms were oxidized, they lost electrons. When reduction of one species happens at the same time as the oxidation of another, it's called a redox reaction. Since electrons generally don't move around on their own, we can be pretty sure that if we see a reduction taking place for one entity, there'll be another entity in the same reaction that's being oxidized. We now have the tools we need to describe redox reactions. Here we have the reaction of copper with silver nitrate, forming copper nitrate and silver. We start off with copper in its pure form, copper atoms bonded together with metallic bonds. And we have a solution containing silver ions and nitrate ions, Ag+ and NO3-. When we add the copper to the silver nitrate solution, there's a beautiful reaction. Crystals of silver grow on the surface of the copper, and the solution starts to turn blue. Since copper can form ions with different charges, we have to use the II notation to indicate we're dealing with copper 2+ ions. The copper atoms we started with lost electrons, forming copper 2+ ions. At the same time, the silver plus ions from solution gained electrons, forming silver atoms. The copper atoms lost electrons, so they were oxidized, while the silver atoms gained electrons and they were reduced. So we can see which species was reduced and which was oxidized, but it could also be helpful to talk about the species that does the reduction or does the oxidation. For this, it might be helpful if we write the net ionic equation. We can start by writing out the full ionic equation, where we've separated out the salts into their cations and anions. The nitrate anions don't participate in the reaction. We can see they're unchanged, identical on the reactant and product side of the equation. If we remove spectator ions and get the net ionic equation, it'll be easier to see where electrons are moving from and where they're moving to. Each copper atom in the reaction is donating 2 electrons, one to each of 2 silver plus ions. One way of expressing this is that Ag+ is reduced by copper. This is because it's copper that's giving up the electrons that are received by the Ag+ ions. But simultaneously, since it's the silver plus ions that are receiving the electrons from the copper, we can say that the copper is being oxidized by the silver plus. We can look at this another way and say that copper is the reducing agent, the component of the reaction that's responsible for reducing another species. Likewise, we can say that silver plus is the oxidizing agent because its presence causes another species to be oxidized. A reducing agent, or a reductant, is a substance that reduces another substance during a redox reaction. As a result of this reaction, the reducing agent is oxidized, while an oxidizing agent, or oxidant, is a substance that oxidizes another substance during a redox reaction. And an oxidizing agent, because it oxidizes something else, is reduced as a result. So in this example, copper will be oxidized and silver plus will be reduced. Copper will be the reducing agent and silver plus will be the oxidizing agent. And the copper 2+ ions will be the product of oxidation and the silver atoms will be the product of reduction. Now that we've looked at the mechanics of reduction and oxidation and redox reactions, let's have some practice. Consider the equation shown. Cl2 aqueous plus 2Br- aqueous react to form Br2 aqueous plus 2Cl- aqueous. A. Which arrow shows reduction? B. Which arrow involves a loss of electrons? And C. Which arrow involves the gain of electrons? The arrow in all 3 questions refers to either A or B. In the equation, we can see the chlorine molecule, Cl2, reacting with the bromide ion, Br-. forming bromine, Br2, which dissolves readily in water, producing a memorable orange colour, and chloride ions, Cl-. To make it easier, you can separate the individual processes. So A refers to Cl2 transforming into 2Cl-, and process B refers to 2Br- transforming into Br2. Here, I'm ignoring the state symbols. In process A, we see a molecule of chlorine composed of 2 chlorine atoms, transforming into 2 chloride ions, each with a charge of 1-. Therefore, this process reflects the addition of 2 electrons, 1 to each of the chlorine atoms. And for B, we have 2 negatively charged bromide ions, transforming into neutral bromine atoms in a bromine molecule. Therefore, B corresponds to the process of removing 2 electrons. Question A refers to reduction. Reduction is the process of gaining electrons. This is easy to remember if we use oil rig. Oxidation is loss, reduction is gain of electrons. Therefore, the answer to part A is arrow A. In arrow A, chlorine is being transformed to chloride by the addition of electrons. This is reduction. Part B asks us to indicate the arrow that involves a loss of electrons. This is arrow B. In process B, we have 2 bromide ions being transformed into bromine, losing 2 electrons. And finally, the answer to part C is arrow A. In reaction A, chlorine is gaining electrons to form chloride. Next, let's look at a question involving ionic equations. Which of the following statements about the following ionic equation is incorrect? Zn solid plus 2Ag plus aqueous react to form Zn2 plus aqueous plus 2Ag solid. A. Zinc atoms becoming zinc ions is oxidation. B. Silver ions becoming silver atoms is reduction. C. Zinc acts as a reducing agent. D. Silver ions gain electrons. Or E. Zinc atoms becoming zinc ions is reduction. In this reaction, we have zinc in its elemental solid form reacting with silver ions in solution. And our products are zinc ions in solution and solid silver. Our job is to examine the statements and find the incorrect statement. The first statement is that zinc atoms becoming zinc ions is oxidation. We can use our mnemonic, Leo the lion says grr, to tell us what oxidation and reduction are. Leo expands to the loss of electrons is oxidation, and grr expands to the gain of electrons is reduction. From the equation, we can see zinc is being transformed into zinc 2+. This corresponds to the removal of 2 electrons. We can also see silver plus ions transforming into silver atoms. This particular process involves 2 electrons being added. We can see that zinc atoms in this case are becoming zinc ions and losing electrons. This statement is true, therefore it can't be our correct answer. Next, we have silver ions becoming silver atoms is reduction. We can see from our equation that the silver ions are gaining electrons, forming silver atoms. Therefore, this is reduction, and this statement is true, and therefore not our correct answer. The third statement requires a little bit more insight than we've got thus far. Zinc acts as a reducing agent. What's a reducing agent? A reducing agent reduces something else by giving it electrons. We can see from the equation that each zinc atom is giving up 2 electrons, 1 each to 2 silver plus ions. Since it's giving up electrons, it's acting as a reducing agent. So this statement is also true. And since we've already discussed that it's the silver ions that receive the electrons, we know that silver ions gain electrons is a true statement, and therefore not our correct answer. The last statement suggests that zinc atoms becoming zinc ions is reduction. But we know that in this process, the zinc atoms are losing rather than gaining electrons. So this is not reduction, this is oxidation. So of the 5 statements given about the ionic equation, the only one that's incorrect is that zinc atoms becoming zinc ions is reduction. Finally, let's finish up with the key points. Reduction is a process where a substance gains electrons, while oxidation is the reverse, the process where a substance loses electrons. At higher levels, we may move away from counting electrons to looking at what we call oxidation numbers. A redox reaction is a type of reaction in which reduction of one substance and the oxidation of another substance occurs simultaneously. The reducing agent is the substance in a redox reaction doing the reducing of something else. As a result of this, it is oxidized, while the oxidizing agent is the substance in a redox reaction that is oxidizing something else and that is in turn reduced.